Okay, we're going to be looking at a application which is really kind of cool. I really like to finish the course with this investigation of dynamical systems, and in particular Markov processes, because it's a very applicable thing. And this is just the sort of tip of the iceberg. You can take entire courses on dynamical systems and on Markov processes. So let's talk about it and then see how it works and look at a couple examples. So a dynamical system, what is that? It's just literally a finite set of variables whose values change with time. So here's some examples. We might be interested in how the percentage of voters who are registered, Republican, Democrat, Independent, or some other party changes over time. We may be interested in how the population is changing in a city and its surrounding suburbs. For instance, we might want to know the percentage of people who are commuters versus or commuters that drive themselves versus people who use public transportation, especially in a big city. There's other areas where we're interested in in sort of genetics, how certain characteristics are passed down to the next generation. What percentage will have different colored eyes. I don't know what percentage will have certain other characteristics. And the list goes on and on. There's examples in the book of a lion preserve, and there's different zones within this vast preserve, and they want to track and know the movements of the lions or animals or whatever they are over time. So lots of different situations. The bottom line is we have different quantities or variable quantities whose values change with time. And I'm just going to illustrate this with a simple example. So in this example, suppose we have two competing television channels. Now, in this day and age, we have so many ways of watching things. Then TV channels is really changed. When I was growing up on TV, I think we had I can count maybe 9 channels. That's it. Of course, I had to change channels not with a remote control, but I had to get up and turn a knob on the television. But things have changed. But let's keep it simple. Let's suppose there's only 2 channels. Everyone wants one of 2, and let's say initially that 50% of the viewer market in time watch channel 1 and channel 2, so it's split evenly. And then we're going to assume that over each 1-year period, channel 1 captures 30% of channel 2's share, and channel 2 captures 20% of channel 1's share. What is each channel share after 1 year? So the way I'm going to set this problem up is to help us not just answer this one question, what is it after 1 year, but the questions that we will look at, which is what will happen after 2 years, after 3 years, etc. What's the pattern? So in order to set that up, I'm going to assign 2 variables, x sub 1, and I'm going to emphasize it's a function of time here. Let's let this be the channel 1 share, t years after the initial point in time. X sub 2, same thing, just channel 2 share, t years after the initial point in time. Okay, so what do we know from the problem? First of all, I know that initially at time 0, right now, each have 50%. So both of these quantities is equal to 50% or 0.5. Okay, now we do have something about, each year we're going to assume some viewers switch allegiance, so to speak, from one channel to another. And I'm going to do this with a diagram. There's only 2 channels, so it makes the diagram very simplistic in a way. This will be channel 1 over here, and this will be channel 2 over here. And what we have is that initially, assume after every 1 year period, channel 1 captures 30% of channel 2's share. So that means 30% of the people watching channel 2 will switch to channel 1. So that'll mean, I'll draw it this way. I'll draw an arrow over to channel 1, and we'll put in 30%. Okay. Now, what I like to do is also to realize if 30% of channel 2 viewers are switching allegiance to channel 1, then what do we know about the remaining 70%? They are staying with channel 2, and the way I indicate that is sort of a recircling back arrow. So 30% switch, 70% stay. In the same way, we can say what? Channel 2 captures 20% of channel 1 share, so going from channel 1 to channel 2 we have 20%, and that means what percent is going to recycle back and stay with channel 1? That's 80%. So this is a diagram we can draw, and it's somewhat helpful to visualize the process. Okay, but what I'm going to say then is from this we can say the following, that the viewer share of channel 1 1 year later, so when t is 1, is going to be what? Okay, well, first of all, 80% of the channel 1 viewers stay with channel 1. So 80% of the channel 1 viewers initially, right, which is x1 in year 0, right, therefore we'll have 80% of those staying with channel 1 a year later. But we also gain what? 30% of channel 2 viewers. So here's 30% of channel 2 viewers from year 1. And x sub 2 of 1 is what? Well, channel 1, we gain 20%. 20% of channel 1 from the previous year, and 70% of the viewers stay. Okay. So now if I want to actually do the calculation here, I can do it because I know 50% for each of these quantities. We'll just go ahead and do that. And I get 40% here plus 15% is 55%. Over here for channel 2, I get, what's this going to be? This will be 10%. All right, 10% here. And this will be 15%. So 10% and 15% is, I knew something was wrong because I'm not adding up to 100% here. It's 0.7. 35% plus 15% plus 10%. I'm just all over the world here. 10% and 35% is 45%. I knew it was 45%. I knew these had to add up to 1, but my mind is not functioning well this morning. Okay, but there it is, and so you can see the net effect after 1 year. But my interest is, what if this trend continues? So year after year, assuming that these rates maintain, right, every year, 30% leave channel 2 for channel 1 and 20% leave channel 1 for channel 2. What's the trend? What's going to happen? What is the changing values to these variables? Well, we can see the relationship here, and that is, I'm going to write it this way, that if I know what the rates were in the previous year, I'll say that year n, say, then I can predict n plus 1 the next years, right? And the way that I'm going to do that is what? 80% of viewer channel 1 share, right, from the previous year, right? Plus what? 30% of channel 2 viewership from the previous year. X2, the next year, will be what? 20% of channel 1 from the previous year plus 70% channel 2 from the previous year. Now, what do we have here? You might think we have a system of linear equations, right? And I'm going to write this in matrix form. I'm going to call the vector x at n plus 1, this is just the time again, is equal to some coefficient matrix. I'm going to, instead of using A, I'm going to use P, and we'll say Y here in a minute. And this is times x to the n. So, and this is going to be if x of n is what? The x1, x2. That's our variables that are changing, right? The vector of those variables. And P is our coefficient matrix. And in this case, the coefficient matrix is what? Okay. And you know, so notice this trend. I can find the next year by multiplying by this matrix. It's almost like a matrix transformation, if you will. I just multiply the previous year's vector, if you will, containing the quantities, the percentages for each variable for that previous year, and I'll output the next year's. So for instance, if like we did, if I want to find year 1, I'm just going to do P times year 0, the initial amount. And year 2 will be P times year 1. And year 3, P times year 2. Whoops. P times year 2, and so on, right? So that's going to continue on that trend. And notice, though, as well, that in looking at the year 2, which is P times x1, but x1 was what? P times x0. And P, notice, is going to be, in this case, a square matrix. So P times P, I can write this as P squared times x of 0. And you see the trend there. What's it going to be for year 3? It's going to be P cubed times x of 0. And so, you know, from this trend, you know, to continue, we see that P, we see that x to the n plus, well, let's just do x to the n, is equal to what? If it's 3, it's P cubed. If it's 2, it's P squared. It's equal to P to the n times the initial values of the vectors there. Sorry, I'm not doing well this morning. Okay. So, you know, here's the observations we make about this. So this matrix seems to be pretty important, and this involves probabilities, basically. We can think of this, you know, the fact that 30% switch to channel 1 roughly translates into, in any given year, there's a 30% chance that a viewer 2 person will swap to watching channel 1. And there's a 70% chance that a viewer 2, channel 2 viewer will stay with channel 2. So these are probabilities, and this is a probabilities matrix. We're going to use the letter P for that. So let's detail all these things and talk about what we've just observed. So the values of the variables in a dynamical system at a point in time are referred to the states, or the state of the variable at that time. And so the states that we had here were just channel 1 and channel 2, and so the values we had are like the initial state had what? 50% for each one. After 1 year, the states were what? 55% for x1, 45% for x2. So these are the states. If we have n states, we'll denote them s with subscript 1 to s to subscript n. So we only had 2 states here. We will say in general n states. Now the probability that a member of the population will change from state J to state I, you know, like channel 1 to channel 2 or vice versa, is denoted Pij, where Pij is between 0 and 1. inclusive. If the Pij is 0, if the probability is 0, then the member is certain not to change from state J to state I. If the probability is 1, then the member is certain to change from state J to state I. And the collection of such probabilities can be arranged in what's called the transition matrix, right? And that's that P that I called before, the transition matrix here. Now notice the notation. Pij is the probability of switching from what? State J to state I. J to I, so column to row essentially. So notice I like to go from and designate these columns, and then rows are the 2's. So this means P12 is the probability that you switch what? From state 2, notice that's the second number, to state 1. Okay, P21 is the probability you change from state 1 to state 2. Okay, so it is important we can construct this, but we have to have this structure to it in order for it to work. Now, at each transition period, each member must either leave or stay, right? You either have to stay in the state or leave. We had 2 channels in the last example, so you either stay with channel 1 or you leave channel 1. But this means that the sum of the entries in any column must equal 1, right? Because leaving state 1, you either stay with state 1, right? P11, that's the probability you stay with state 1. Or you're going to switch to state 2, or you're going to switch to state 3, or all the way down to state N. You're going to do one of these things. So the add up all these probabilities has to be 100%, right? You're either going to stay or you're going to go, and so those must be 1. So if I add down any column, I'm going to get 1. Any matrix where that's true and whose entries are non-negative is called a stochastic matrix. Stochastic probability, or stochastic refers to, a probability approach. Probability approach to calculating things. So stochastic processes are done in that way, and a very important thing in lots of areas outside of mathematics. I mean, engineering and the sciences, but also things like just calculating insurance premiums or loan rates or etc. Anything with probability involved in it. Gambling, games of chance, etc., etc. So that's what this is. This is a stochastic process as well, sometimes called. The state vector, we'll call it x of t, is the n by 1 matrix representing the value of each of the n states at time t. So my state vector for our example was this, right? The values of the viewer 1 share and viewer 2 share. By multiplying x on the right by p, we obtain the new population distribution for the states after one transition period. That's what we were saying here, right? When we multiply the previous year by p, we get the current year, or to get the next year, we take the previous year and multiply it by p. And I'm saying year here, whatever the transition periods are. They could be years, they could be months, days, whatever the application is. Now, such a process is called a Markov process. And this is in honor of Andrei Markov, who's a Russian mathematician known for his work in probability theory. And a dynamical system undergoing a Markov process is called a Markov chain. Now, I don't know all the details, but what I understand is that Markov was actually using this process initially to analyze poetry and word distributions and letter distributions, and I'm not exactly sure what, but he was analyzing a poem, from what I understand, by Pushkin, a Russian poet, called Eugene Onegin. And I'm not a poet, maybe you are, and you might be familiar with this work, but it's kind of interesting that his work in poetry analysis gives us a branch now of mathematics that is really robust and rich in all sorts of applications, way far from just poetry. And so he's given the name Markov process and a system that's dynamical, right? Dynamical just means changing, right? So we have the states are changing over time. This is called a Markov chain. So long-term behavior of Markov chains. So if P is the transition matrix, then we look at x of 0, P times x of 0, P squared times x of 0, P cubed times x of 0. What's that? Well, these are the different, we said what? The different time periods, right? So x of 3 is p cubed x sub 0. And so in general, x sub n, right, is p to the n times x sub 0. And so what is this approach? Well, if this sequence converges, so this is a sequence of vectors, if it converges, right, to say a vector q, we call q the steady state vector of the Markov chain in steady state. So in other words, are we approaching, and we go back to this problem, over time, will the percentages share for channel 1, channel 2 become constant, where they're sort of in equilibrium, that each year from there on out, the same percentage are watching each channel, even though we still have 30% swapping from 2 to 1 and 20% from 1 to 2. Do we have a steady state solution over time? And the answer to that can be asserted in a couple ways. Now, in this case, if we do have a converge to some vector q, right, that contains those steady state solutions, if you want to, we call that the steady state vector, then the sequence of matrices p times p squared times p cubed approaches a matrix q, each of whose column is q. And so that's very interesting that the sequence of this n by n matrix, as we take bigger and bigger powers of it, is approaching a fixed matrix q, where each column is identical and each column is equal to the steady state solution. Okay, so if we do have a steady state solution, that happens. Now, when do we have a steady state solution? We don't always. I mean, here's a simple example of when we don't. Say 100% of the people swap from channel 1 to channel 2 and 100% swap from channel 2 to channel 1. If we have, say, 60% initially watching channel 1 and 40% watching channel 2, and basically 100% switch, we're just going to swap between what? 40 and 60%, right? The vector would be 40%, 60%, and then what? Swap it 60%, 40%. And then the next transition period, swapping back. So we just swap back and forth continuously. We would never reach a steady state solution. So that's sort of a silly example, but that can happen. So when do we have one? So first of all, a stochastic matrix P is said to be regular if P or some power, P squared, P cubed, or whatever, has all positive entries. Okay, so no zero entries. We can't have negative entries, right, in these matrices because they're probabilities. Could have zero, but P or some power P has all positive entries. If that's the case, then P is said to be regular. So a sufficient condition for a Markov chain to have a steady state solution is that the transition matrix is regular. And such a Markov chain is called a regular Markov chain. I'll just have you go back to our transition matrix for the example we did. Notice there are all the entries are positive. No non-zero, no zero entries. So this system is going to have a steady state solution. I can tell right away. Okay. Well, let's do a more interesting problem then. Actually, I'm going to break the video here and we'll restart it with this example.